It's my great pleasure today to introduce Kirthevasan Kandasamy today for our Bayesian optimization speaker series. So Kirthi is a postdoc at UC Berkeley, and he now works on sequential decision-making under uncertainty, game theory, and computer systems. And in the topic of Bayesian optimization, my impression is that he never fails to provide very elegant solutions to problems like high dimensionality, batch evaluation, and multi-fidelity problems. So today he's going to tell us about resource allocation in multi-arm bandits. Let's welcome Kirthi.
All right, thanks for having me, Z, and thanks for the nice introduction. It's a pleasure to be here, yeah, thanks for having me. So, right, so this talk is about resource allocation in multi-arm bandits. It's joint work with some awesome collaborators at Berkeley. So it's Bridgen, Ion, Mike, Ken, and Joey. And there are some more collaborators at the end that I will mention, but most of the work I'll be covering in this talk is work with these folks. Right, so multi-arm bandits at a high level, what are we trying to do, right? We're trying to optimize some unknown systems. So there's a decision maker over here, and that's interacting with an unknown system. And every time, on every round, the decision maker recommends some arms to be pulled, and then you obtain these observations, and then you keep repeating, usually with the goal of optimizing this system. And it has a variety of applications in, hyperparameter tuning, optimizing distributed systems, materials discovery and drug discovery, and then scientific simulations and so on. So for instance, if you're tuning hyperparameters, each arm pull would be some recommendation, some configuration you want to test, and the observation would be like how well the model is doing, what is the accuracy, and you want to find the model with the highest accuracy. If you're in like drug discovery, each arm would be some candidate drug you want to test, and your observations could be the candidate's specificity, and so on, and potency and so on, right? But bandit problems are usually formulated in terms of the number of arm pulls. So usually people study this notion called cumulative regret, which I'm assuming many of you are familiar with. So the cumulative regret after T rounds is the sum the difference between the optimal arm and the arm which you recommended on round T. And then you sum this over T rounds. And a slightly different setting for bandits, which will be the focus of this talk, will be on best arm identification, where you want to identify the best arm with probability at least 1 minus delta, but you want to minimize the number of arm pulls in doing so. But the main idea is in both of these settings, you're usually formulating the problem in terms of the number of arm pulls or the number of samples. So I will be using these terms, sample complexity and number of arm pulls, interchangeably throughout this talk. And usually, the settings come in two different flavors. There are sequential settings. So for instance, if you're try to do hyperparameter tuning in your training a machine learning model, you have, let's say you decide that you need 4 GPUs to tune this model. You would try out one configuration for a certain amount of time, then you would try out the next configuration and keep going like this. And every time you make a decision, you're using information from past trials in order to come up with recommendations for future trials. And you have also these batch parallel settings where you might have, if I give you 64 GPUs, then you would come up with 16 parallel runs, 4 GPUs each. And once again, every time you make a decision, you're making a decision for all of these parallel trials. And you're using information from all previous rounds, right? So there's a reason why we like to formulate bandit problems in terms of the sample complexity. And this is because it usually translates to the amount of resources you consume, which in turn is translate to cost and time and ethical concerns and so on. But the main theme for this talk is going to be that we usually care about time and cost, and often the number of samples does not directly translate to these considerations under practical constraints. And formulating bandit problems directly in terms of these constraints, these time and cost constraints, can give rise to new algorithms, theory, and also, as we'll see, some better empirical results. So there are two specific settings that we are going to look at in this talk. In the first setting, we are going to look at systems that have sublinear scaling. So you have, let's say in this previous problem that I told you, where I gave you 64 GPUs and asked to find the best hyperparameter configuration. And we decided for some reason to go with this allocation of 4 GPUs per configuration. But you could ask yourself, is this the best way to allocate resources among these different trials? In particular, you could come up with an allocation that looks the following form. So let's say you have 3 different arms or 3 different configurations you want to try. You could decide, I'm going to try out all 64, all resources, all 64 GPUs for one trial at one go. The experiment finishes in a short amount of time. Then I'm going to try the next configuration and keep going. Alternatively, you could come up with a more parallel strategy where you use a few amount of resources for a single trial, but that takes a long amount of time, and do something like this on the right figure over here. Or you could try to do something a little bit more interesting that maybe looks something like this. And I'll get into the trade-offs of these different strategies later on in this talk very soon. So the second setting we are looking at is elastic resources, and this is of course inspired by like the popularity, the recent popularity in cloud computing platforms. So I remember when I started off my PhD, grad students were trying to fight for these limited amount of spots on the compute cluster, but over the last few years, we've come to now come to a situation where people are running experiments on the cloud, and you would usually use something like GCP or AWS, Azure, and it's very common nowadays to see people running experiments on the cloud. But yet the way we run experiments on the cloud is exactly the way we run experiments on a fixed compute cluster. So you would buy a bunch of machines, pretend that it's your small mini cluster, and then execute this, and then run your bandit algorithm or any other problem on this fixed amount of resources. But what the cloud offers you is elasticity. And what that means is you can scale up or scale down the number of trials you want to do at a certain time. So at the beginning, you might decide, I want to use, I want to try out, these 4 different configurations. And at the next round, you decide, I want to try out more configurations. So you spawn a bunch of VMs on your cloud platform. And then at the next round, you decide, I don't want to try out as much trials. So you kill some of those VMs, and then you try out fewer trials. And then you keep proceeding in this fashion. And the reason you want to scale down is because you want to reduce cost. And the reason you want to scale up is because if you want to try out different trials, then you might want to scale up. So in both of these experiments, the total resource time you have used is the same, but the allocation of these resources is very different. And what we really want to explore in this setting is, what does elasticity have to offer when you're at least in the context of bandit problems. And as we'll see, there are other natural applications outside of cloud-based experiments for this framework. Okay, so here's what we're going to do in this talk. I'll first talk about, I'll spend a little bit of time reviewing best time identification, because that will be the setting for most of this talk. And then we'll talk about best time identification with a fixed amount of resources and sublinear scaling. Then we'll talk about best time identification with elastic resources. So these are the 2 settings that I mentioned right now. And then depending on how much time I have, I will also go into some work we have been doing on hyperparameter tuning with elastic resources. And so these are the papers that kind of cover, that I'll be covering, and some of them are still under review, but some of them are appearing at ICML and this year, and EuroSys. So EuroSys is a systems conference where we've published this work. Okay, so yeah, just a reminder, if you have any questions, feel free to interrupt me. But is the talking clear? Am I going too fast? Is everything all right so far? Okay, sounds good. All right, so let's get started with best time identification. So in best time identification, you're given a bandit problem new of n arms. And when you pull arm I, you observe a reward from this distribution nu I. So I'll be using this notation nu to denote the arms, and nu I will denote the distribution of arm I. And arm high, so this distribution has mean mu I. So you can think of each arm as a candidate or some configuration that you want to test, and putting an arm corresponds to an experiment. And we'll assume that mu1 is greater than mu2 is greater than or equal to mu3, and so on. So arm1 is the best arm, right? And best arm identification is basically you want to identify this best arm. So you're given some delta in 0, 1. Again, you can think of delta in 0, 1 as like a target failure probability. So you want to identify the best arm with probability at least 1 minus delta. And you want to do this by pulling arms to collect information about their mean values. And obviously, as I said, these experiments are quite expensive, so you want to keep the number of arm pulls to a minimum. There's a slightly different variation of this called the path version of this problem. So here you're given some epsilon greater than 0 and some delta, and you want to identify an epsilon optimal arm with probability at least 1 minus delta, where an epsilon optimal arm is an arm which is within epsilon of the optimal arm.
Yeah. One quick question.
Yeah.
What was X in the expectation?
Oh, X is simply you're drawing a random sample from this distribution UI. Is it this that you were referring to? Or?
Yes.
Yeah.
Right.
Yeah. It's just a random sample you draw from this distribution, and then yes, exactly. Yeah.
I see. So each nu is actually a distribution for the value of the arm, right?
Right. Yeah. So you can think of each nu I as a distribution, and your collection of distributions are be denoting by nu. So.
Thanks.
Yeah. Right. Okay, so here's a class of algorithms for best arm identification. They're called these racing style algorithms. And I think the first paper to kind of introduce this was this paper from 1993, but here are a couple of more papers. There are other papers that do it too, but here are a couple of more papers that like are more, modern instantiations of this idea. So here what you have is you have, let's say these are your arms, and I've denoted the mean value by its height. So this is the best arm, this is the second best arm, and so on. And what you do is, so you don't know the mean values. So what you can do is you need to collect samples, and when you collect these samples, you can try and infer what their mean values would be. So what these samples would allow you to do is construct confidence intervals for these arms. And the reason you're obviously constructing confidence intervals here instead of just looking at the mean is because you want to reason about the uncertainty in the observations. So based on these observations, you've constructed these confidence intervals, and if your confidence intervals are doing the right thing, they should trap your true mean with high probability. And then what you can do with these confidence intervals, you can look at the arm with the highest lower confidence interval. And then you can say with high confidence that if the upper confidence interval of an arm, so like these two arms, for instance, is the upper confidence bound is smaller than this lower confidence bound, then you can conclude that with high confidence that these arms would not be optimal. So what you can do is you would eliminate these arms, and then in the remaining rounds you would just go on to sample from these from the remaining arms, the surviving arms over here, and then you would keep repeating this process. So just to recap, these are your arms. The arms are unknown. You would collect samples, and at each round you would construct these confidence intervals. Then and then you would eliminate the arms whose upper confidence bound is below the best lower confidence bound.
A quick question.
Yeah.
Is Thompson sampling a soft version of this?
Is Thompson sampling a version of? I wouldn't really say so. Yeah, I mean, besides the obvious difference between these confidence intervals are more frequentist and Bayesian, but even besides that, I wouldn't really call this a version of Thompson sampling. So, yeah.
This is an action elimination technique.
Yeah, it's more like an elimination technique, right? Yeah. So. Right.
Okay.
Yeah. Okay. So these are racing algorithms, and then right. And so what do we know about best arm identification? The number of samples required scales on the order of h of nu times log 1 over delta. So delta is the probability with which you want to identify the best arm, and h of nu is the sum I equals 1 to n 1 over delta I squared, where delta I is the arm's gap value. So if your arm so delta is simply the difference between the optimal arm and the ith arm, except if I is the optimal arm, in which case it's just the difference between the optimal arm and the second optimal arm. Right. So for example, if we go back to this problem, right, if the arm gaps are small, it means intuitively it seems clear to us that you would require a lot of samples in order to identify the difference between these arms. If the arm gaps are large, you can do this with a fewer samples. And one of these classical results from statistics and hypothesis testing tells you that you require usually on the order of 1 over delta squared samples in order to identify the difference between two means that are delta apart. And so in here, what you have is something very similar, except you have n arms. So you're just summing these things from I equals 1 to n and the 1 over delta squared. Right? And then for the packed version of this problem, the result is very similar, except h of nu is of the form I equals 1 to n, 1 over delta I plus epsilon squared. So there's a plus epsilon over here in this h of nu term in the packed version of this problem. So you'll notice here that I will have used a big theta tilde. So the tilde is because I'm hiding a bunch of like logarithmic and subpolynomial terms over here. And the theta is because these are both upper bounds and lower bounds. So the upper bound is usually like a racing style algorithm will get this sample complexity. And then lower bounds, you can also show that this amount of samples are necessary in order to like do well on this problem. Okay, so that's so that's best time identification. Do people have questions over here? I think this is a good point to pause for questions.
Yeah, I have a question on the previous page. So for the theoretical result, so if we extend it to like infinite arms, does it mean we need infinite number of queries in order to identify?
Right. So if you have an infinite number of arms, what you usually have to do is impose some kind of like structural assumption on the problem. So if you just have an infinite number of arms and there is no information you can share between these arms, then there isn't a lot of hope. But if there is like some assumption, like a Gaussian process assumption, for instance, where you assume that these arms are smooth across some kind of Euclidean space, or any other kind of assumptions, then you have hope of doing slightly better. So
right, I see.
Yeah. So usually in like GP bandits, we are more accustomed to like formulating theoretical results in terms of the cumulative regret and then like translating that to simple regret. But so best time identification is a slightly different take on this problem. So yeah.
So maybe I also have a quick question. Maybe you will answer this later on. But these arms are for you stateless entities, right? They don't have a state.
Right. So these arms are stateless. Yes, that is correct. So I know that some work, especially like in the Bayesian setting and like using Gittins indices and so on, they assume like there is a state that's changing every time you pull arms. But here these arms are stateless. You're right. Yeah.
Okay. The reason why I was asking because you mentioned this problem of hyperparameter tuning, and chances are that sometimes these guys really are stateful entities where you keep training those guys and sort of the reward the average reward will actually change depending, for instance, on how many times you play that arm.
Right. No, I think that's absolutely correct, especially if you have like keep training like in a continuous fashion. And so the way we formulated this problem, depending on how much time we have at the end, for the hyperparameter tuning version, it's slightly different from the way we formulated the problem for the best time identification. For best time identification, like the motivation for the formulation comes from very classical statistical techniques, whereas for hyperparameter tuning, we followed some of these work on like hyperband and so on in order to formulate the problems. So
I see. Thank you.
Yeah.
I also ask a quick question / comment about the previous question.
Yeah.
So in general, is it correct to say that in order to have results like these, the space of arms should be compact in the sense that in the discrete case where there is no geometric relationship, you have to have finitely many arms, and in the continuous case, it has to be bounded, for example, inside a Euclidean space?
Right. So in the continuous case, I think at a high level, what you want is structure between the arms, and like that structure can come in like various forms. And one form is, of course, there is a Euclidean space, and you assume your function is smooth. So if you query one point, you know that the function value around those points are also close to the value that you queried. But in general, you could have like any type of structure, provided you can like define some kind of metric or like some distance between like the different arms. then there is some hope for doing well. It doesn't have to be a Euclidean space, if that answers your question. So
you just need a finite covering covering number of the metric space, basically.
Right. So if you want theoretical results, then yes, you do want to define like a metric, like a covering number, and so on. Yeah. Okay. So let me get moving. So right. So the first setting we are going to look at is best arm identification with a fixed amount of resources and sublinear scaling. So just going back to this slide that I put up previously, said, you have a fixed amount of resources. And you have to decide how to allocate resources between your arm pools given this amount of resources. So you could say I'm going to, for instance, you could say I could come up with a strategy where I do this sequentially. So I use a lot of parallelism within each arm. We allocate all resources to one arm. Or I could come up with a more parallel strategy across arms where I use fewer resources for each arm, but instead they take a long time to run. So what are the main trade-offs that are involved in here? So usually when you try to parallelize arm pools, they do not scale linearly. And this is because your communication and synchronization costs and a variety of other constraints. And so for example, if you have linear scalings, if you try to come up with this graph of how much time does it take to complete an arm pool versus how many resources you've given, if you have linear scaling, then it's going to scale as 1 over x. So if I give you x amount of resources, then you finish in 1 over x the amount of time that it previously took you. But if you have sublinear scaling, then it's going to take it's going to take you slightly longer, right? Like in the blue curve over here. So why would you want to allocate more resources per arm pool? Because in that case, the arm pool is finished faster, and then we can use that information to make better subsequent decisions. But on the downside, because of this sublinear scaling, the resource usage is inefficient. Whereas if you were to allocate few resources per arm pool, it's the other way around. The resource usage is now more efficient, but now you are waiting for a long time for your arm pools to finish, and therefore you cannot make better decisions. So in this example over here, if you look at just look at these two figures in general, you would find that here, because you were able to do this sequentially, by around with a few pools, you were able to eliminate the green arm because you were able to identify that it is far from being optimal. And now you can, the remaining rounds, you can allocate most of your resources to the red and blue arms. Whereas here, you do run the green arm for a long time, but you're able to execute far more arm pulls because, as I said, things don't scale linearly. And so there's a trade-off here between information accumulation and resource efficiency. That is, which means we have to be careful about how we design the allocation of resources to these different arm pools. Right, so the algorithm we have for this setting is called adaptive parallel racing. So it is a racing style algorithm, which means we pull arms on we proceed over a certain number of rounds and we pull arms on each round. And at the end of the round, we eliminate these arms based on the confidence interval. So just like the figure that I showed you before. But now the way it kind of works is we first, at the first round, we pull each arm a small number of times. And then if the arms that are surviving, we increase the number of pulls for the next round. And then the moment the arm, and if an arm is eliminated, if an arm is eliminated, then we don't pull that arm further on. But what we do is we increase the number of arm pulls for the arms that are surviving. And the rate at which we increase the number of pulls is going to depend on the scaling function lambda. So I'm not going to get into the specific form of the specific details because I don't think that they are the most important thing, but I'm trying to just rely more on like high-level intuition and like ideas. But the idea is, like I said, over here, you increase the number of arm pulls for all the arms that are surviving. And so intuitively, what's going on here? Yeah.
So what is the meaning of resources here is you're not in the fixed budget best arm identification. Each arm has different cost. Is it the better way to think about it, or?
No, so each arm has roughly the same cost. The way to think about it is if I allocate a few resources, then it's going to take a long time to finish. But at the same time, my resource usage is going to be more efficient. And this is because distributed systems do not usually scale linearly. So intuitively speaking, if I were to ask you to train a model on using one GPU, you could do one of two things. You could take one GPU and train it for 1 hour, or you could take 2 GPUs and train it for 30 minutes. And it is usually the case that training with one GPU for 1 hour is going to do better than training with 2 GPUs for 30 minutes or 4 GPUs for 15 minutes, because there is these systems do not scale linearly. So what we want to study here in some sense is this trade-off between, especially in multi-amp bandits, where you're making these decisions sequentially. If you pull a lot of, if you execute few arm pulls and get the results early, you can use that information to eliminate arms. Whereas if you were to use fewer resources, you won't be able to eliminate arms as quickly, but you might get better bang for your buck in terms of your resource efficiency. Does that make sense?
This cannot be transformed to a fixed budget based on identification problem?
Right. So the fixed budget setting we have, I'm actually not going to talk about it here, but if you look at the paper, we do have an algorithm for the fixed budget setting as well. So we call it a fixed deadline setting. So you're given a certain time deadline of T rounds, and you want to identify the best arm within that deadline of T rounds using those resources. But the algorithm is slightly different. It's not an a racing style algorithm like the one that I've mentioned over here.
Okay.
Yeah, unfortunately, I won't get into that algorithm in this talk, but you can refer the paper. So.
Thank you.
Yeah. Right. So intuitively, what's going on in this algorithm is that you kind of pull the arms a few number of times early on because you want to quickly discard the easy arms, and then the arms you increase them because those arms are hard to distinguish between. So you want to invest more resources. And if you're going to invest more resources, you might as well do them in parallel because the resource usage is more efficient. That's intuitively what's going on in here. And theoretical results, what we show is that the number of samples required for best arm identification is scaled with the following quantity. It's script t times log 1 over delta, where script t is the solution of the following dynamic program. So I've graded out because the equation itself is not very important right now, but there is a certain dynamic program, and script t is given by the solution to this dynamic program, where the inputs are the arm gap values. So instead of this sum of 1 over delta I squared terms that we had before, but now we have these 1 over delta I squared terms that go into a dynamic program, and the complexity scales with this quantity. And once again, this is both an upper bound and a lower bound. The upper bound is obtained via the algorithm APR, or adaptive parallel racing. And the lower bound integrates the scaling function into hypothesis testing techniques in order to, we do that in order to obtain the lower bounds. And so here are some simulations, and we use a scaling function of the form lambda 1 over x is proportional to 1 over x to the q, where q is between 0 and 1. And the way it's kind of designed, I said, if lambda of x is 1 over x is 1 over x, it's linear scaling, right? So if q is closer to 1, it means your scaling is good, whereas if q is closer to 0, the scaling is bad. So here we have two simulations where we are changing the difficulty of the problem. So there's 1 over delta to squared. So if it's large, it means the problem is more difficult. We're looking at how much time it takes to identify the best arm. And we are plotting the runtime versus the smallest time for different q values. So here it's q equals 0.9, so the scaling is good. And here the scaling is q equals 1 over is 0.25, so scaling is bad. And they're comparing algorithm APR to batch racing strategies. So these are all the algorithms that use a racing style algorithm, but they use a fixed batch size of either 1, 10,000, or 10,000. And what you find is that our algorithm is able to adapt to problem difficulty and do as well as the best fixed batch size for that problem. So for instance, the red curve, which is our algorithm, is quite low in most of these settings. Whereas if you were to look at the green curve, which corresponds to a large batch size, it does very well on this problem over here, where the scaling is bad. So you want to use more parallelization because the scaling is bad. Whereas here, when the scaling is good, it doesn't do as well. Right. So that's fixed sum identification with a fixed amount of resources. And now let's move on to the elastic setting. Right. So if you were to look at the current literature on pack best arm identification, so here they are solving this problem in the pack setting. So that's probably approximately correct, where you're trying to identify an epsilon optimal arm. the sequential setting, you can pull arms one at a time, and the number of samples scales as h of nu times log 1 over delta, where, as we saw before, h of nu is the following quantity. So what this kind of indicates is that if your arm gaps are large, so your delta values are large, it means the h of nu quantity is going to be small. So you can do really well on the problem. This is like to contrast it with the passive settings. So if I were to tell you up front, you just have one go, you should execute all your arm pulls at one go and identify the best arm. Your best strategy really is to pull each arm like 1 over epsilon squared times, because for all you know, your problem could be very difficult and all arms could be just epsilon away from the optimal arm. And so if you're going to pull each arm 1 over epsilon squared times, then your complexity is going to be n times 1 over epsilon squared times. So what this shows is that sequential algorithms can adapt to problem difficulty because you're pulling one at a time. If you it allows you to quickly eliminate some of these suboptimal arms instead of pulling them like in the passive setting. Instead of pulling them, you might have to pull them a large number of times. But in our work, we are given a certain deadline, and we have to execute. We can execute multiple arm pulls per round, but we have to finish under this deadline. So it's not as bad as the passive setting, but it's not as easy as a sequential setting either. And the question we want to ask ourselves is, how well can we do if we were to be given limited rounds of adaptivity? So there are actually a couple of papers that have studied this setting, but they don't actually talk about the trade-off between the trade-off between the sequential and the passive setting and how these results translate from start going from over here in the passive setting to over here in the sequential setting. And we'll see that our results actually does a better job of characterizing that. Right. So just to kind of ground this a little bit more, if you're in the passive setting, you have t equals 1. It requires a lot of samples, even on easy problems. If you're in the sequential setting, it has small sample complexity as it can adapt to the problem. But on the flip side, this takes a long time, because if you're going to just keep performing these trials one at a time, it's going to take a long time for you. And what we are here is in the elastic setting, and what we're trying to do is try and achieve the best of both worlds. We can hopefully try and finish in a short period of time, and do this with intermediate sample complexity. Right, and applications are, one of the applications I already mentioned to you, it's, you're running, hyperparameter tuning or scientific simulations, but instead of doing it on a fixed cluster, you're doing it on the cloud, where you can scale up or scale down. If you're doing clinical trials, you're trying to identify the best treatment or vaccine among multiple candidates over a few rounds of trials. So, if you're doing a clinical trial, you have the opportunity to try as many candidates as you want. But obviously, you want to reduce the number of trials to reduce costs and for ethical reasons. If you're doing laboratory experiments, you have high throughput experimentation platforms that can be used to conduct several trials at a time. But you want to reduce the number of experiments in order to reduce the cost of reagents. Simply because you can execute many experiments in parallel doesn't mean you want to, because these experiments can be quite expensive. So what these applications kind of highlight is that we are used to this assumption of doing like bandit models in the sequential setting, or using a fixed amount of parallel resources, and that assumption often does not hold true in practice. And by leveraging elasticity, it turns out you can actually do a lot better. Okay, so the algorithm we have for this setting is, once again, it's going to be a racing style algorithm. We call it elastic batch racing. And we're going to proceed over a sequence of rounds. And at the end of each round, we're going to eliminate arms based on the similar idea of looking at these confidence intervals and then eliminating those arms based on if the lower confidence bound of the best arm is higher than the upper confidence bound of a certain arm, we will eliminate that arm. But what we're going to do is we're going to pull each surviving arm roughly this amount of times on round t. So that's epsilon to the minus 2t over t. So so epsilon is, you should think of it as a small quantity. So as little t is increasing, so in later rounds, if an arm is surviving, it means it will get pulled a large number of times. And if an arm survives all the way until round t, then if you substitute over here, you'll see that it gets pulled epsilon on the order of epsilon to the minus 2 times. So this, as I said before, you roughly need 1 over epsilon squared pulls in order to differentiate between two arms. So that kind of gives you what you want. But hopefully, because you're gradually increasing the number of pulls, it will allow you to eliminate these arms, and which means you can adapt to problem difficulty, even if not exactly, at least to a limited extent. Right. So, and in order to characterize this, we present two types of theoretical results. So in the first type, what we show is that this adaptivity can be characterized by using this minimax optimality over subclasses. So, so just as a reminder, in the passive setting, you require n to the n over epsilon squared samples. The sequential setting, you require this h of nu times h of nu many samples, where h of nu is this quantity over here. And in this work, what we want to try and answer the question is how well can we adapt to problem difficulty when you have only limited rounds of adaptivity? And the way we kind of do this is that, so you cannot adapt to this exact quantity over here, but what we show is that we can come up with a partitioning of this problem space into like easy and hard problems. And this partitioning is I've given it over here, and once again I've graded out because I don't want to get into the details. But you basically come up with this P gamma, where gamma is chosen from this set over here. And for each value in this set, you have a subset of problems. And generally speaking, when this gamma value is small, the problems in this subset are easy. And if the gamma values are large, like if gamma is like t, then the problems in the subspace are really difficult. And what we show is that our algorithm can adapt to these subclasses. So they cannot adapt to the specific problems because you don't have infinite rounds of adaptivity, but it can adapt to these subclasses. So if you apply, for instance, our algorithm on a problem nu in P gamma, the number of samples it takes is the highest is scales at the supremum over nu prime in P gamma of h of nu prime. So so it doesn't adapt to h of nu, but if nu is in P gamma, it does as well as the hardest problem in P gamma over here. So this is to contrast it with the passive setting, where even on the simplest problem, you have to do this with n over epsilon squared times, whereas here you just need to adapt to the problem difficulty of that subclass. And we also complement this with a lower bound, where we show that the worst case sample complexity in this class is going to scale with the same quantity over here. So this is the first type of optimality results we provide. The second result we kind of provide is we try to bound how well it will do when compared to a sequential setting. So so what we show is that if you apply our algorithm for any problem, so we're not in the subclass anymore, but if you take any problem, it does as well as a sequential complexity over here, which is what we have over here. But there is an additional epsilon to the -2 over t term that appears over here. So you can bound the number of samples it takes over here. And as you can see, as t goes to infinity, which means you approach the sequential setting, this quantity vanishes, so you approach the sequential term over here. And we also complement this with the low bound, although this low bound has some caveats. We show that for any algorithm that's epsilon delta pec, there is some problem where the number of samples over h of nu is at least as high as this quantity over here. So there are two types of optimality results that this algorithm satisfies, and it basically says that in both cases we kind of demonstrate the fact that when t is really small, you're kind of constrained by these limited rounds of adaptivity, but as t increases, it approaches the sequential complexity. So in this setting over here, as t becomes infinity, this quantity goes to 1, and in this setting over here, like as t gets close to infinity, then this partitioning approaches these individual problems. And once again, here are some simulations. And what we have here is our algorithm, last week batch tracing. We compare it against a sequential strategy in the green curve. The red curve is a passive strategy, and like the black and the orange curves, they are like other baselines that we compare it to. We kind of find that it's doing as you expect it to. It's doing almost as well as the sequential one, but not quite as well. And it's doing better than the other methods. Right, so that is best time identification with elastic resources. I think now is a good point to pause for questions if people have any.
Yeah, maybe I have a quick question.
Yeah.
What's the intuition behind the fact that you don't get the same performance as the fully sequential scenario in the case when epsilon is very small? When epsilon is zero, when epsilon is 0, for instance.
Yeah, so if epsilon is 0, I think, so just think about like the completely passive setting, right? So if epsilon is 0, what can you do? You can pull all arms a certain number. Okay, let's just simplify it and say we just have 2 arms. So you can pull both of these arms a certain number of times. and hope that you can identify the best arm within these number of pools. But if I don't give you like an epsilon threshold, like for however many number of pools, I can set them to be arbitrarily close so that you won't be able to identify the difference.
I do still have the gap between the two, right?
Right. No, you still have the gap, but I can make this gap arbitrarily small. Right. So if you, for instance, like I said, it requires like 1 over epsilon squared samples. So if you come up with an algorithm and on t equals 1, you decide, I want to pull this n times. If I set my gap to be smaller than 1 over square root of n, or the order of 1 over square root of n, then I already I've given you a really difficult problem that you cannot identify with n pools.
I see. So your lower bound essentially is, in worst case, overall possible values of the gap. I understand correctly.
Yeah, the gap, right. So it is over all possible values of the gap. But at the same time, we do require this epsilon constraint because if not for the epsilon constraint, the problem might be infeasible.
Okay, maybe we can take this offline because I was expecting somehow the gaps to play a role in the lower bound.
Oh, so the gaps do play a role in terms of this h of nu quantity over here. So in this quantity over here, the h of nu comes in over here, and h of nu is basically like I said, this term over here.
Right.
I equals 1 to n delta I plus epsilon. So the gaps do play a role, and you can adapt the problem difficulty. So like, for instance, in this result, you come up with this partitioning based on the gaps. And so this partitioning is such that, some problems, like some of these classes in the partition are easy, some of these classes are really hard. And we show that we can adapt to each of these sub-problems in the partition.
But in fact, the partitioning as epsilon goes to 0 becomes trivial, right? The way, if I understand correctly. And we should take this offline because this is too many details. Yeah.
Right. Yeah, I think I agree. Right. Yeah.
All right.
Okay. Let me see. How much time do I have? Okay, I think I have enough time. So, all right. So finally, what we're going to talk about is a little bit of work on hyperparameter tuning with elastic resources. Okay, so here it's slightly different. So this kind of goes back to one of the questions that we mentioned before. Is we want to tune hyperparameters, and usually, especially since this hyperband paper that came out a few years ago, the common approach for doing this is to train some models for a certain amount of time, look at their intermediate accuracies, and then carry forward the trials that do well on this problem, and then eliminate the trials that are not doing very well. And if you were to implement hyperband using a fixed amount of resources, so let's say we have 8 GPUs and we're using a single GPU each, your strategy might look something like this. So you need to complete in under 10 minutes. You start off by trying out these different trials. You eliminate these trials that are not doing very well. So these are the gray ones that I've shown over here. And the trials that are doing very well, you take forward, and you might decide to start out new trials. But at some point, because you have a finite deadline, you might decide, okay, some of these more promising trials, I should give them more resources to see how well they're doing. And eventually, the final trial, I'm going to spend a lot of time just training it just to see what the accuracy is. But in an elastic setting, you might try out something or the policy that we have looks something like this. So we have the same resource time constraint. So it's 8 GPUs times 10 minutes. So it's 80 GPU minutes. Here also we have 80 GPU minutes. But because you can scale up or scale down, we start off with a large amount of resources. And then if the accuracy values are not very good, we kill those jobs. And the models that are doing well, we can continue training till the very end. So why is elastic strategy helpful in this specific setting for hyperparameter tuning? And this is mostly because it helps circumvent a lot of undesirable effects of sublinear scaling. So this kind of ties back to the first theme that we mentioned, the first setting that I mentioned earlier. And just to illustrate this, I've shown you the accuracy when you train these different models, VGG16 and ResNet15, using a budget of 40 GPU minutes. But we do this for different resource and time. So the first setting, we train it for 1 GPU and 40 minutes. The second with 2 GPUs at 20 minutes, and all the way up to 8 GPUs at 5 minutes. And what we find is that yes, using more resources in parallel is helpful. But if you have to constrain yourself to the same resource time, then using a few amount of resources and training them for longer is usually more desirable than using more resources and training them for a short amount of time. So what that will allow you to do in this setting, for example, is that when you are constrained to work with just 8 GPUs, you also have to deal with like a bin packing problem. You need to somehow figure out a way to allocate these resources within like a tight constraint. And therefore, you need to take this resource, like take this configuration and expand its parallelism. And then, depending on how well it's doing, and when you increase the parallelization, you give it more resources, which is nice. But now you're not using your resources as efficiently as possible. And what the elastic setting we found to help you to do is that it will help you avoid these effects of nonlinear scaling, because you can take a configuration and train it all the way. And if a configuration is not doing well, you don't have to think about reallocating these resources. You can just simply kill that trial and then take forward those trials that are doing well on the problem. So here are some results that we have for image classification. So we have like several baselines over here. We have random, Asha, hypershed. This is like a Bayesian version of hyperband. And our method is called SEER. And what we also have is this elastic version of hyperband and elastic version of grid search. And on all these problems, we see that SEER is doing quite well. But quite interestingly, the elastic versions of these methods are already doing a lot better than the fixed resource versions of these methods. So this kind of illustrates why we should be thinking about the elastic setting, especially now that people are increasingly moving their jobs and their workloads to the cloud. Even like naive extensions of the algorithms are doing better than some like well-designed, like sophisticated methods for like fixed resources. So this is on image classification. This is on text classification and image segmentation. And the takeaways are pretty much exactly the same. SEER is doing quite well, but so are the elastic methods or like elastic variants of these some of these prime methods. Right, so that's the end of my talk. So what did we see in summary? So usually bandit problems are formulated in terms of the number of pools or the sample complexity, but carefully considering resource constraints that arise in practice can give rise to algorithms, theory, and better empirical results. And we looked at two settings where we had a fixed amount of parallel resources, but with sublinear scaling. And the second setting, we looked at elastic resources. And the elastic setting is something that, in the lab, we are kind of interested in because there is increasingly, as I said, people are moving to the cloud, but the way we run experiments or the way we run jobs on the cloud is just by pretending that it's a small cluster and they're running on the cloud. Whereas the elasticity gives you a lot of opportunities to be a bit more flexible and therefore do better. So that's pretty much about it. These are my collaborators. So in the first row, we have collaborators for the work on best time identification. And on the second, third rows, we have my collaborators for elastic hyperparameter tuning. So that's it. Thank you very much.
Yeah, thank you so much, Kirthi. This is really, really cool. So yeah, everyone, if you have questions, please unmute or raise your hand.
Hi, I have a quick question about the fixed round setting where there's only T rounds. It seems like what you would do is like on the first round allocate like a constant number of pulls per arm, and in the second round you would increase the number of pulls per arm that you think should still be there and eliminate the bad arms.
Right.
Is that true? And then if that is true, how does the number of pulls increase per round? Does it like double or increase at a specific schedule?
Right. So just to be clear, you're referring to this algorithm, right? For in the fixed resource setting.
Yeah, the fixed round where you have T rounds. I think it's that one.
Or is it the elastic setting where you have T rounds?
Yeah, the T rounds setting. Between the passive and sequential. Yeah, this.
Right. So so the rate at which we increase the arms increases at the following rate: epsilon to the minus 2t over t. So if an arm is eliminated, then we don't pull that any further. But if an arm does survive, then we bump up the number of pulls on the order of epsilon to the minus 2t over t.
Oh, is there a reason why that rate is like intuitive reason why that rate is the correct rate?
Intuitively, it's like yeah, it turns out, is there an intuitive reason for this? Not that I can think of. Yeah, at a high level, what you want to do is like, you want to increase the number of pulls. That seems intuitively clear. Why is it exactly epsilon to the minus 2t over t? Yeah, we tried out a bunch of different ways to kind of model this. I think there are a few kind of constraints that we have to, respect when we're doing this. The first is that at the end of t rounds, you have to do this epsilon to the minus 2 times. Because if an arm survives, then it could be close to being epsilon optimal, and therefore you want to be able to differentiate it. But besides that, I think we tried out a bunch of values, and it turns out that if you were to use this schedule, then it gives you this like 2 nice optimality properties, and we decided to go with it. So.
Okay. Yeah. Thanks.
Yeah.
So one question. So now that you have time, can you elaborate a little bit on how these ideas can be extended to the fixed budget setting, and which algorithms from the fixed budgets, like the successive reject or any of that you get and modify for this setting?
Yeah. So well, actually, we did not study the fixed budget setting in the elastic setting, but we did study the fixed budget setting in this fixed resource but sublinear scaling setting. And in the fixed budget setting, the algorithm we kind of built on was the successive halving algorithm. So in a successive halving, if you're familiar with, you pull all the arms a certain number of times. So if you're given a certain budget, I think you split that budget into like log in different brackets, and each bracket you pull them a certain number of times. You eliminate the worst half of the arms, and then in the remaining rounds you keep eliminating half of the rounds until you have like 1 arm remaining. Right.
Okay.
But what we found in the fixed resource setting was that it's usually not always the best idea. May not be to just split your time into like log n brackets. Rather, it might be you want to still kind of operate in the same setting as successive halving, but it might make more sense to like combine these brackets, because by combining brackets you might actually end up executing more pulls because of sublinear scaling. So if your scaling is poor, you might want to combine these brackets and get better results.
And another question is, if the goal changes from best arm identification to some other properties of these distributions, I don't know, estimating the mean or so, do you think how difficult would be tackling those problems? And
yeah, I think this is like a really interesting open question. It's one of those things that we have we've been wanting to think about for some time. Yeah, I think best arm identification was like a nice starting point to kind of like think about what is the best way to allocate resources, but there is like a lot of problems in like sequential decision making under uncertainty, and it's unclear at all at this point like, what the best way to allocate resources is. So I think there's a lot of work to be done in this space. So, yeah.
Thank you.
So I actually have a question about the last part of hyperparameter tuning.
Mm-hmm.
So for so are we assuming that each training loop are consuming or taking, for example, 1 GPU or fixed amount of GPUs, or is it changing dynamically during training?
Right. So in our algorithm, what we kind of do is we come up with a schedule where we come up with a resource allocation upfront. So here, for instance, we say, like for some trials, they're going to start off with 1 GPUs. For some trials, they're going to do with 2 GPUs, and so on. And what you're kind of trading off between here is, should you use fewer resources for a configuration and try out many different configurations, or should you use more resources per configuration and try out fewer resources and fewer configurations in general? And if your problem is such that you can quickly identify, like if you start training, you can quickly identify the optimal configuration, then you might prefer to use. So if the problem is such that it's fast to train the model, then you might prefer to try out several trials with few resources per configuration. Whereas if your problem is such that in order to be able to even get to close to optimal, you need to train it for a longer time, you might prefer to allocate more resources per configuration. And like usually a priori, you don't have any way of saying this. So the schedule, what it kind of does is it kind of hedges its bets and tries out like different trials, like different resource allocation strategies. So here it has like this budget of 80 GPU minutes. It has used 40 GPU minutes for using just a single resource or like a single GPU for a trial, and like 40 GPU minutes for using 2 resources per trial. But because you're using more resources, you don't try out as many trials in these settings where you're using 2 GPUs per trial. So it tries out like with a different schedule and then tries to see which does best.
I see. So it's not changing. So at the beginning of this trial, it selects a certain number of resource, and then it's using that fixed resource to finish till like the training is finished. Right?
Yes, exactly. Yeah. So the plan is in some sense chosen ahead of time, and the moment you give me your deadline and your budget, then I will come up with a plan already. But changes in between the algorithm is which arms are you eliminating, and you might decide to like switch configurations between these different trials depending on how well they're doing. So yeah.
But do you actually observe noisy outputs or noisy evaluations for different hyperparameters?
Right. So here we are kind of like it's the sequential like training strategy that people use for they're training neural networks. So you keep training them, and you look at the intermediate accuracies, and if the intermediate accuracy is not very well, you eliminate it. And if the accuracy is doing quite well, then you keep training it. So yeah.
I see. So it's so it's not going to evaluate the same hyperparameter twice.
Right, it is not going to do that. Yeah, so it's not going to do that because in like machine learning training, these evaluations do tend to be fairly noisy, but the noise usually comes from your initial random sampling techniques, your initial random sampling more often than the randomness in your stochastic gradient updates. At least this has been our experience. So it's usually safe to assume that if a trial is doing well in the early stages, it might continue doing well in the later stages as well. So.
Got it.
That assumption doesn't always hold true, and we found counterexamples to it, which is why we have to come up with a more interesting resource allocation strategy. But yeah, in general, like it's not noise in the stochastic sense, if that is what you're
doing. So. Yeah. So I have another question, but I want to see like if people have other questions. All right, I'll ask them. So I wonder, like for I guess especially for the second part, there are a lot of different bounds for the cumulative regret, or like number of samples.
Yeah.
So is there any assumption on, for example, the distribution of the values for the arms? Or anything that's being used in these bounds?
Yeah, so I think one assumption we are making is that the noise is sub-Gaussian. So I did not kind of get into those details in this talk, but we're assuming that the noise is sub-Gaussian. So that is basically the only assumption that we are making on the problem. So.
I see. How well do you think that match like empirical results or empirical applications?
Yeah, so it's that's always an interesting question. I think sub-Gaussian assumptions are quite standard in this literature, so we kind of stuck to those assumptions. It holds true in some of these experiments we tried out as well, but there are also like situations where, like as one person mentioned, there isn't a lot of stationarity, so you can't just assume that you're just sampling from a fixed distribution all the time. And sometimes these distributions tend to have longer tails, so sub-Gaussian assumptions do not work. But like the former is a bit more difficult to address. The latter, I think you just need to come up with construct these confidence intervals appropriately. So usually in order to like construct these confidence intervals, you're using the sub-Gaussian assumption. But if you have like longer tails, you would construct like wider confidence intervals, and I think many of these ideas would still carry through. So.
I see. Thanks.
Yeah.
All right, anyone have other questions? All right, well, if not, I guess we can wrap up. Yeah, thank you so much, Kirthi. This is really a great talk.
All right, thank you very much. Yeah.